The Channel Tunnel is a great example of what people can achieve. This underwater passage is an amazing piece of engineering that has changed how we travel and trade. The Channel Tunnel, which people often call the Chunnel, is 31.4 miles long. That's 50.5 kilometers. It goes under the English Channel, about 150 feet, 45 meters below the seabed. This incredible tunnel connects Folkestone in Kent, England, to Coquelles, near Calais, in northern France. Building the Channel Tunnel was a huge job. It took thousands of workers and engineers from both Britain and France working together. They built massive tunnel boring machines, nicknamed Le Shuttle and Britannia, just for this project. These machines dug the tunnel through the chalk marl under the seabed. These giant machines, each weighing over 1,000 tons, were amazing for their time. They could dig through the earth very quickly while putting in concrete segments to line the tunnel walls. People have wanted to connect Britain with mainland Europe for a very long time, even before the Channel Tunnel. People started talking about building a link as early as the 18th century. In 1751, a French engineer named Nicolas Desmarets drew the first design we know of for a channel tunnel. Then, in 1802, Albert Mathieu, a French mining engineer, had another idea. Even though it was difficult with the technology they had, people kept thinking about a channel link throughout the 19th century. The invention of steam power and better tunneling technology made people even more interested in the project. What was happening in the world during the 19th century also affected the Channel Tunnel project. Napoleon Bonaparte, when things were peaceful with Britain for a short time, thought a tunnel link was a good idea. Even though it was difficult to get everyone to agree, everyone knew a channel link would be good for business. The Industrial Revolution meant that there was a lot more trade and travel between Britain and the continent. In 1875, Britain and France started a company called the Channel Tunnel Company. To try to finally build the tunnel, the company started drilling on both sides of the channel, which were the first real steps towards building the tunnel. Even though there were problems and delays, people never gave up on the Channel Tunnel dream. In the 20th century, new technology and politicians who wanted to work together brought the project back to life. The invention of tunnel boring machines, or TBMs, which could dig through hard rock very accurately, changed everything. After World War II, people were more interested in European unity and cooperation. In the 1980s, British Prime Minister Margaret Thatcher and French President François Mitterrand decided to try the Channel Tunnel project again. They signed a new agreement in 1986, which allowed private companies to pay for the tunnel. Designing the Channel Tunnel was a huge job. The engineers had to figure out how to build something that could handle the massive pressure from the sea above. The first step was to carefully study the seabed of the channel. They decided to build 3 separate tunnels next to each other, 2 for trains and 1 in the middle for service. This 3-tunnel design meant there was a backup and a way for maintenance and emergency vehicles to get through. Each of the 3 tunnels was designed with a specific size and features for its job. The 2 running tunnels, which are 7.6 meters in diameter, were built for high-speed passenger trains and freight trains. The service tunnel, which is smaller at 4.8 meters in diameter, was very important for the tunnel to work. It had important systems like ventilation fans, pumps and communication cables. Fire-resistant doors and a special ventilation system kept everyone safe in case of a fire. The Channel Tunnel engineers had to deal with some very unusual problems because the tunnel goes under the English Channel. They had to freeze the ground in some places where there was water mixed with the chalk marl. The depth of the tunnel also caused problems. The engineers used very strong concrete reinforced with steel fibers to handle the immense pressure from the water. They also put flexible joints in the tunnel lining every so often to allow for any ground movement from earthquakes. These joints mean the tunnel can move a little without breaking. Building the Channel Tunnel was a massive project. It showed how clever and skilled humans can be. The most important tools were the tunnel boring machines, like giant mechanical earthworms digging through the earth. The TBMs used in the Channel Tunnel project were amazing for their time. They had a massive disc with hard teeth that chipped away at the chalk marl. As the disc rotated, it dug into the earth, making a circular tunnel. The dug-up material was then carried back along the tunnel to the surface to be disposed of. Building the Channel Tunnel wasn't just about using a lot of force. It was like a carefully planned dance of engineering precision. As the TBMs moved forward, they placed precast concrete segments to line the tunnel walls. Once they had a ring of concrete segments in place, they filled the gap between the lining and the surrounding rock with a special mixture called grout. The construction of the Channel Tunnel never stopped, with teams of engineers and workers working day and night. The work was physically tough and required a lot of skill and accuracy. Steering the TBMs through the Earth's crust with pinpoint accuracy was an amazing feat of engineering. The machines used a clever guidance system that combined laser beams and electronic distance measurement. Surveyors, positioned at regular intervals along the tunnel, used laser beams to create a straight line. The TBMs, which had laser targets, could then tell where they were in relation to these beams, making sure they stayed on track. This level of accuracy was crucial for keeping the tunnel straight and ensuring a smooth track for the high-speed trains. As the TBMs got closer and closer, everyone eagerly awaited the moment when the two sides would meet. On December 1st, 1990, this historic event finally happened and the workers and engineers celebrated. The last step was to equip the tunnels with everything needed for trains to run. The Channel Tunnel officially opened on May 6, 1994. The tunnel made travel between Britain and the continent much easier, making journeys shorter and bringing people and businesses closer together. Digging a tunnel under the sea, even one as shallow as the English Channel, presents unique challenges. The weight of the water above puts immense pressure on the tunnel, and even a small leak could be disastrous. Engineers had to design a strong, flexible tunnel lining to withstand water pressure and ground movement. They used high-performance concrete reinforced with steel fibers. A waterproof membrane was added behind the lining for extra protection. Air pressure inside the tunnel was kept slightly higher than outside to prevent leaks. A sophisticated ventilation system maintained this balance. While the chalk marl formation that ran along much of the tunnel route was relatively easy to excavate, other geological formations posed significant challenges. In some sections, the TBMs encountered layers of harder rock, such as sandstone and limestone, which slowed progress and increased wear and tear on the machine's cutting heads. The engineers had to adapt their approach, modifying the TBM's cutting tools and adjusting the excavation parameters to cope with the varying ground conditions. In other areas, the TBMs encountered pockets of water-bearing strata, posing a risk of flooding. To mitigate this risk, the engineers employed a technique known as ground freezing. This involved drilling boreholes into the ground ahead of the TBM and circulating a refrigerant solution through them. The refrigerant solution lowered the ground temperature, freezing the water in the surrounding soil and creating a solid barrier that allowed the TBM to excavate safely. Another challenge was the presence of methane gas, which can be hazardous in enclosed spaces. Methane detectors were installed throughout the tunnel to monitor gas levels, and ventilation systems were designed to dilute and extract any methane encountered. The TBMs were also equipped with methane detectors and shut-off mechanisms that would halt excavation if gas levels reached dangerous levels. The engineers' ability to anticipate and overcome these geological challenges was crucial to the project's success. Their expertise in geology, geotechnical engineering and tunneling techniques allowed them to adapt their approach as needed, ensuring the tunnel's safe and efficient construction. Building a tunnel as long and complex as the Channel Tunnel required an unprecedented level of coordination between the British and French teams. The two sides had to work together seamlessly, sharing information, expertise and resources to ensure that the tunnel met in the middle with pinpoint accuracy. One of the key challenges was the difference in tunneling practices between the two countries. The British team preferred to use open-faced TBMs, which allowed them to see the tunnel face but were more likely to have the ground collapse. The French team preferred closed-faced TBMs, which were safer from ground collapse but made it harder to see the ground conditions. They compromised, with each side using its preferred TBM type for its section of the tunnel. Another challenge was the language barrier. While many of the engineers and workers spoke both languages, making sure everyone understood each other at all levels of the project took a lot of effort. They had interpreters at meetings and on-site to help people communicate, and they translated technical documents into both English and French. Despite these challenges, the British and French teams built a strong working relationship, united by their shared goal and purpose. The success of the Channel Tunnel project shows how powerful international collaboration can be and the ingenuity of the engineers and workers who made it happen. The Channel Tunnel is a testament to human endeavour, combining innovation with determination. Its completion marked a pivotal moment in engineering history, pushing boundaries and inspiring new engineers. The project triumphed over technical challenges, showcasing the ingenuity of thousands of engineers and workers. Tunnel boring machines were used on an unprecedented scale, boring through earth with precision. These machines excavated millions of cubic meters of chalk marl, installing tunnel lining as they progressed. The TBM's performance exceeded expectations, proving large-scale mechanized tunneling's viability for future projects. The accurate alignment of the 3 tunnel bores over 31.4 miles was a remarkable feat. Using laser guidance and precise surveying, the tunnels met in the middle with an accuracy of just a few inches. This precision was essential for the safe operation of high-speed trains. The project showcased innovative ground engineering techniques like ground freezing and compressed air tunneling stabilized the ground and prevented water ingress. These techniques were invaluable in overcoming the project's geological challenges. The impact of the Channel Tunnel goes far beyond its physical structure. The project led to many technological advancements in tunneling, surveying and construction management, leaving a lasting impact on civil engineering. The knowledge and experience gained from the project have been used in later tunnel projects around the world, influencing the design and construction of major infrastructure projects. The development of high-performance concrete, specifically designed for the tunnel lining, was a significant technological advancement. This concrete, reinforced with steel fibers and designed to withstand immense pressure and resist cracking, set a new standard for tunnel construction materials, paving the way for the use of advanced materials in other demanding engineering applications. The Channel Tunnel project also highlighted the importance of effective communication and collaboration in large-scale engineering endeavors. The project brought together engineers, geologists, surveyors, and construction workers from Britain and France, requiring them to overcome language barriers, cultural differences, and technical challenges to achieve a common goal. The lessons learned from this international collaboration have influenced the management and execution of subsequent large-scale infrastructure projects. The Channel Tunnel stands as a symbol of human ingenuity, a testament to the power of collaboration, and a source of inspiration for future generations of engineers. Its legacy is not only the physical link it created between Britain and mainland Europe, but also the technological advancements, engineering innovations, and international partnerships it fostered. The Channel Tunnel is more than just a tunnel, it's a triumph of human ambition, a testament to engineering skill and a symbol of international cooperation. It represents our age-old desire to overcome obstacles and connect with the wider world. This marvel of modern engineering, born from centuries of dreaming and decades of planning, has fundamentally changed travel and trade between Britain and mainland Europe. The tunnel has shortened distances, strengthened economic ties, and made the dream of a spontaneous weekend trip to Paris a reality for millions. Beyond its impact on transportation, the Channel Tunnel has left a lasting impact on the field of engineering. The challenges overcome and the innovations pioneered during its construction have pushed the boundaries of what's possible in tunnel engineering. The project has led to advancements in tunneling techniques, materials, science, and project management, leaving a legacy of knowledge and expertise that continues to shape major infrastructure projects around the world. The Channel Tunnel reminds us that even seemingly impossible things can be achieved with creativity, determination, and the desire to connect.